Let's solve question number 29 of chapter 9 from the section Center of Mass, Linear Momentum and Collision from the book S.C. Verma. The question says, figure shows a small block of mass small m which is started with a speed v on the horizontal part of the bigger block of mass capital M placed on a horizontal floor. The curved part of the surface shown is semicircular. All the surfaces are frictionless. Find the speed of the bigger block when the smaller block reaches the point A of the surface. The question can be solved in a single step, but my main concern is to go through the details of the question, the modifications that can be made, and the misconceptions attached to this question. The question says, the small m block is sliding to the left and we need to get the velocity of the bigger block when the smaller block reaches the point A. If the question was find the velocity of the bigger block when the smaller block reaches here or any point on this horizontal part, if we'll take the bigger block separately, it will get a force of normal from the ground and mg. They are balanced. All the surfaces are frictionless, so there is no friction here, no friction here. So there is no net external force acting in the horizontal direction. Initially, the bigger block was at rest. In the absence of any net force, its final velocity will also be 0. Same is the case for the small m block. If there was friction here, but no friction here, then if we'll take the small m block, it's sliding to the left, so force of kinetic friction will act on the right. So this is m into a1. Equal and opposite force of friction will act on the bigger block to the left. So that is F equals to m into a2. From here we can get a1 and a2. And if this distance is given, then we can use v squared equals to u squared plus 2as and can get the value of v, provided we are taking everything relative. If time is given, we can use v equals to u plus at and get this velocity. But as the block comes to the curved part, it presses the bigger block with a normal force of n and in turn gets a normal force n. This n can be resolved into two components. Say this is theta, so this is n cos theta and this is n sin theta. Now, on the bigger block, a net horizontal force is acting this way, n cos theta. Say this is n1, this is n2. In the vertical direction, there will be one more force, n2 sin theta, and they will be balanced. That is n1 will be n2 sin theta plus mg. As the block moves upwards, the normal force goes on changing. This angle goes on changing. So, in this case, this net external force in the horizontal direction goes on changing. So we can't solve the problem taking the blocks separately. When the forces are not clearly known or are changing, the tool available to us to solve the problem is conservation of linear momentum or center of mass. And for both of this, we require a system. First, let's solve the problem using conservation of linear momentum. For this, the system that we will choose should be isolated, that is, no net external force should be acting on the system. As long as we are in the horizontal part, we can take the blocks as separate systems because there is no net force acting on this. There is no net force acting on this. So we can use conservation of linear momentum taking the blocks separately. Once the block reaches the curved part, external forces go on acting and we can't take these two as systems. If we will take both of them as a system, these all forces are equal and opposite, so they will cancel out. Even if there is friction, that will be equal and opposite. This is frictionless, so we can take both of the blocks as a single system and use conservation of linear momentum. For this system, the force acting in the horizontal direction is zero, but in the vertical direction, gravity goes on acting, so linear momentum will be conserved only in the horizontal direction, not in the vertical direction. When the smaller block reaches the point A, let's put an observer at the point A. The observer will find that the block is only moving vertically upwards, that is not having any horizontal velocity. So, velocity of small m with respect to capital M, because we have attached the observer to capital M, is Bm minus B capital M. These are with respect to the ground. If we'll observe from the ground, then this block, as it's getting a net horizontal force of n cos theta towards the left side, will move to the left. This one will be moving to the vertically upward direction, so also in the horizontal direction, so it will be moving in this direction. So this Vmg is Vm I cap, as it is in the negative direction, it's minus, plus the vertical component Vm j cap minus this one is Vm I cap, as it's in the negative direction, it's minus. This is minus Vm I cap plus B capital M I cap plus B small m j cap. This is minus Bm plus B capital M I cap plus B small m j cap. This is the relative velocity of m with respect to capital M, as the observer is saying that the horizontal velocity is 0, so this component is 0, minus B small m plus B capital M is 0, or B capital M is B small m. Let's say that is some velocity V. So at the point A, the horizontal velocities of the blocks are the same. This can be taken this way also. For this observer, this block is moving only vertically upwards. At the point A, both the blocks are in contact. So, if the velocity of the smaller block is higher than the velocity of the bigger block, then this block will pierce through the bigger block, that is, will enter into the bigger block. If this one's velocity is smaller than this one's velocity, the contact will be detached. Now let's use conservation of linear momentum to the system of blocks. Initial momentum of the system was m into v plus capital M into 0 because this block was initially at rest. The velocities of the blocks at the point A are the same. Let's say that velocity is v prime. So that is mv prime plus capital M v prime. So this is m plus capital M into v prime is mv plus 0, that is mv. So v prime is mv divided by m plus m. This is the answer. Now let's solve it using center of mass. As there was no force acting in the horizontal direction to the system, the velocity of the center of mass in the horizontal direction will remain constant. Velocity of the center of mass is given by m1 v1 plus m2 v2 divided by m1 plus m2. Initial velocity of the center of mass BCM1 is m into v plus capital M into 0 divided by m plus m, which is mv by m plus n. This is equation 1. Final velocity of center of mass BCM2 is mv prime plus capital MV prime divided by m plus n, which is m plus m into v prime divided by m plus n. As the velocity of the center of mass remains constant, these two are equal. So mv by m plus m is equal to m plus m into v prime divided by m plus n. Cancelling m plus m, we get v prime is equal to mv by m plus n. Now let's see some of the misconceptions that are there in this question. Many people think as this block moves to the left, this block moves to the right, which is not the case. In the previous problems of SC Burma, there were cases that there was a boat floating on water and a man was moving to the right. As the man moves to the right, this boat was moving to the left. But these two cases are totally different. Here the friction was static. Here the friction is kinetic. The person here was pressing this boat, totally different from this case that this block is sliding on this floor. This block will never move to the right, even if there is friction between these two blocks. As this block moves to the left, kinetic friction will act on this block to the right, and equal and opposite kinetic friction will act on the bigger block to the left. So on the bigger block, there is a net horizontal force in the left hand side, so it will move to the left. This one's velocity will go on decreasing, but this block will never move to the right. So both the blocks in all situations will move to the left only. This can be verified this way also. The horizontal velocity of the center of mass was mv divided by m plus m. This velocity was towards the left, so the center of mass was moving towards the left. As there is no net external force in the horizontal direction, the velocity of the center of mass will remain constant. that is, it will be towards the left only. Another misconception that people carry is for any point in this curved part, the horizontal velocities of the blocks are the same, but this is not the case. For both the blocks to be in contact, it's not the horizontal or vertical velocities which determine the condition for both the blocks to be in contact. For any point on this curved part, the horizontal velocities are not the same. Only at the point A, the horizontal velocities are the same. As the block moves in the curved part, for the contact to be maintained between the blocks, the velocities along the common normal should be the same. This block moves this way, so its component in the normal direction is 0. The bigger block gets a force this way, which is resolved in the horizontal and vertical directions. So the bigger block tends to move in horizontal and vertical directions. But as it tries to move this way, the ground comes into play and it gives a normal force. Let's say this is N1, this is N2, there is mg. So mg plus N1 is N2. The vertical force is balanced, so the velocity in this direction is 0. It gains only a velocity in the horizontal direction, this way. So the velocity in this direction, that is along the common normal, is 0. We can see the velocities along the common normal are 0, that is, are the same. So the blocks are in contact. If we will resolve the velocity of the smaller block into directions, this is v1, this is v2, and the velocity of the bigger block is v3, then v3 is not equal to v2. These two happen to be equal only at the point A. If we will resolve the velocity of the smaller block v into two components v1 and v2, then due to the horizontal component of this normal reaction, the value of v2 will go on decreasing. Due to the horizontal component of this normal reaction, the value of v3 will go on increasing. If the question is to find the value of v3 at any point in the curve other than the point A, let's say at the point C, then with this much of data, the problem can't be solved. To find v1, v2 or v3 at any point in the curve or even at the point A, to find the value of v1, we require work energy theorem, the details of which we will discuss while we'll be going through question number 61 of H.C. Verma. If you have any concerns regarding this question, you can post your queries in the comments. You can also contact me. This is Sachidanand Rath, phone 099450 You can mail me at sachinrath123@gmail.com. The contact details are also given in the description. You can also contact to attend live classes for class 11, 12, NEET and JEE Mains. If you find the video helpful, please like the video and subscribe to the channel so that this video will be available to others. As YouTube doesn't understand concepts, and a video with the above misconceptions will come in the search engine. This is how YouTube works. Thanks for watching.